Great, it looks like it's 9 o'clock, so we'll get started. Hopefully all of you online can hear me. All right, so I was just talking to Ellie here. So I don't have the exams finished yet. I have your class graded, but I found some mistakes in the multiple choice, which I think possibly threw people off. So I'm going to finish grading the other sections before handing out scores and figure out exactly what's going to happen with that. So expect to get the exams back. I hope to have them like totally done and handed back to everybody. For sure, I'll hand you back the paper exam next week for sure. I'll probably be able to post scores before then, and then you can drop by and grab your exam if you want sometime before then. So for sure we'll get them back next week. I apologize that I don't know, I got them all graded and was looking through the scores and kind of going back over things, and I'm just not happy with some of the stuff on my end, not on your end. So I need to make sure that that's all straightened out and that kind of know the best way to handle that. So hopefully that will be in the relatively near future, but for sure expect to get the paper version back next week. All right, so week 9, which is wild because we only have 14 weeks. So I think we're all officially allowed to start the countdown. We're going to be transitioning, and this week is kind of the start of that transition, a little bit away from, because we're still going to do some of this. We're going to transition a little bit away from cycle problems and thermodynamic cycles. That was kind of the first, I guess a little bit more than half of the course. And we're going to start to try to dig into a little bit, we'll feel like a little bit more of the theory and try to develop a little bit better understanding of where all of this stuff comes from and what some of these terms and stuff that we've been using actually mean, and how would we measure something like enthalpy or internal energy or entropy. Where do we get these numbers anyway? Where do they come from? What do they mean? So we're not going to get all of the way there today's class, but that's where we're headed a little bit. We're going to be transitioning away from, let's take numbers from the steam table and plug them in and solve energy balances and do that. We're going to be transitioning a little bit away to where does some of this stuff come from. Now that we know how to use it, how to do things with entropy, how to do things with enthalpy. We're not going to get there, as I said, just today. This is going to be kind of the rest of the semester. That's what we're going to be focusing on. Today what's going to happen is we're going to do some, we're going to be doing two different cycle problems, and hopefully this will help to show you all a little bit the generalizability, it's a fun word, generalizability of the process and ideas that we've been talking about. So there are 2 videos for this week. One is on the Brayton cycle. We touched on this, probably don't remember anymore. We touched on the Brayton cycle 2 weeks ago before the exam. Right, it was, just touch on it briefly. When we looked at kind of some of the practical aspects of a power cycle, like the steam cycle, we said, well, okay, so what do we know from the stuff that we've done? Well, a higher high temperature and a lower low temperature are better. So we want to ideally get the highest high temperature that we can and the lowest low temperature that we can. So we design different things like cooling towers, or we put our power plant by a lake or a river or Lake Michigan, something like that, to get our low temperature consistently low. But we kind of can't go below ambient temperatures, whatever that happens to be. And then for the high temperature, we're limited in steam power plants. We're limited by the practical aspects of a steam plant in that you're making really high temperature and really high pressure things, and that's just inherently dangerous. So we're limited by kind of materials aspects and just the inherent danger of continuing to raise temperature and pressure. But we still have a lot of temperature to play with, and that's where the Brayton cycle comes in. It's the standard air cycle for power generation. So if you're making, it's the natural gas power plant cycle. And it allows us, as I talk about in the video, it allows us to start to access some of these higher temperatures. Like natural gas, the combustion temperature is 2,000 degrees. We want to get up closer to that. We want to get out of this like 500 to 600 degree C range, and we want to bump up over 1,000, 1,500 type degrees. Raise that high temperature as much as we can. And what happens when you go through in one of your homework problems and actually solve one of these Brayton cycle problems, what you'll see is it basically looks really similar to what a Rankine cycle would look like. There's an air inlet, there's a compression. It's not a pump now, it's a compressor because it's a gas. There's what we would call a boiler. Now it's not a boiler because we're not boiling anything, so it's just the combustion chamber of the turbine, or the combustion chamber of the system. And then there's a turbine where we're actually extracting work. And when you go through and you analyze the different points in this, the same way that you would analyze for steam, the same problem, you just change your stuff in Cat 3 from water to air or nitrogen or something like that. When you go through and analyze it, what you find is the exhaust temperature is still really, really hot. So what that means is, right, we can take a system like this, like a steam power, instead of just a natural gas power plant running just a Brayton cycle, we're going to combine the Brayton cycle with a steam power plant cycle, with a Rankine-like cycle. And we're going to combine these two so that we can use the really high temperatures, but we can also use kind of the, I guess, what would be called medium temperatures. And that's something, again, we showed this, or I showed this last week, where we have we're going to be looking modern natural gas power plants, have a setup at least generally like this. This is what the Holland power plant looks like, where you have there all the way on the left is the combustion turbine. It's really a compressor, combustion chamber, and turbine all in one. And then you have a boiler. That's the really tall, what they call the heat recovery steam generator. That's simply the boiler. That combustion turbine is generating electricity. The waste heat from that turbine goes as the heat source, QH, for the boiler, for a second system running a Rankine cycle. So it's a way to be able to use a broader range of temperatures in our system. And it boosts our practical, like in practical terms, both a Rankine cycle by itself, we're stuck at about 40% thermal efficiency. A combustion turbine by itself, we're also stuck at about 40% efficiency. If we put these two together into a combined cycle like this, we can get up to about 60%, actually a little above 60%. So practically for the same amount of fuel, we get 50% more energy. So it's a huge bonus. I mean, 50% more energy for essentially free. I mean, you have to build extra stuff and you have to, there's some costs with that, but essentially we get 50% energy, 50% more electricity for no extra fuel costs. So that's why combined cycles, if you're building a natural gas plant, you're going to be building a combined cycle plant. The only areas that plants that are not combined, or systems that are not combined cycle plants, the only places that those are built are for what they call peaking power plants. So, right, there's kind of the power demand over time goes up and down as, people come home, everybody turns on lights and washing machines and dishwashers and stuff and air conditioners, and power demand goes up. So to meet some of those spikes, sometimes they'll have just a system that operates. Sometimes they're called peaking plants. There's I think 3 or 4 here in Holland at different areas. There's one up on James Street. There's one kind of south, I think, along 40th Street, just south of campus. There are a couple around the area that they mostly don't run, but if they really need extra power, then they can flip it on. Other than that, the large-scale power plants, those are basically all combined cycle because of the added efficiency for no extra fuel costs. So you'll go through a kind of the details of a system like that and be able to see kind of the nuts and bolts of how that works and how those fit together. Be able to do it without, hopefully, we'll kind of use different parts of problems that we've solved before so we don't have to reinvent the wheel. But I think it's useful to be able to see how those things can connect. The other thing that we're going to be talking about in one of those extra videos is, okay, so if we think back, this is a long time ago now, we had 2 different versions, I guess, of the second law. Right, version 1 was we called the Clausius statement of the second law, and I'll just draw the block diagram. Sorry, not that. And right, this is QL, QH. We said, Clausius said that we can't take heat and move it from a cold temperature up to a high temperature without any work input. And the other statement of the second law that we had was Kelvin Planck. And Kelvin Planck said kind of the opposite. Kelvin Planck said that we couldn't take heat from some high temperature reservoir and turn it perfectly into work. So the 2 kind of tweaks that we could make on that was we could say, and I'm going to draw this here in blue. So these are the 2 different statements of the second law, Kelvin Planck and Clausius. What we said is we could do something like this, where we added work into a system, and then using that work, we moved heat from a cold temperature to a high temperature. And for Kelvin Planck, we could take heat, we could convert some of it to work and then lose the rest or waste the rest. TL. So what I've drawn in blue now are the 2 cycles that we can actually do. In black are the 2 different statements of the second law. Now in blue, that's what we can do. We've focused so far only on the right-hand side, taking heat, turning it into work. In this second video that's posted, we're gonna dive a little bit deeper into the left-hand side and see what actually has to happen functionally in order to do what's shown there on the left. To take heat from a cold area, make the cold thing colder, and the hot thing hotter by adding work into the system. Right? Functionally, we all know this as a refrigerator or an AC unit or a freezer, a cooling process like that, where we're taking heat and the inside of your house gets colder. The part that we don't think about as much is that then outside has to get hotter. Right? So that's why when you walk past an AC unit, you get hot air blown on you. That's what's happening right up here at the top. That's outside. And down here at the bottom, that would be the inside of your house. What's kind of cool about it is, okay, so for Kelvin Planck, we said, what's in that black box? And that's what we focused a lot on. What is in that black box? The ideal thing on the right-hand side in that black box is what? What's the best black box we could have?
Carnot.
The Carnot cycle. So what's the best black box we can have on the left-hand side, which is the same thing but going the other direction? Everything's going the other direction. Take the Carnot and reverse it. Draw the arrows the other way. So that's exactly what we're going to do on the left-hand side. And we can make a reverse Carnot called the Carnot refrigeration cycle. It's literally taking the Carnot cycle, flipping all of our arrows the other way. What was once a pump now becomes a turbine. What was once a turbine now becomes a pump. Everything just flips and reverses and does the opposite of what it was doing before. So what was once the condenser now becomes a boiler. What was once the boiler now becomes a condenser. Everything flips roles. And when we flip roles like that, then we get to an ideal refrigeration cycle. What do you think might be a problem with the ideal refrigeration cycle? All of the same things that were problems with the ideal power generation cycle. So like the Rankine cycle, we can kind of make practical concession. Like, it's not easy to design a compressor that deals with vapor or liquid mixtures. Same thing for the refrigeration cycle. So we're going to do the same kinds of things and say, okay, so practically what can we actually do? And instead of having a reverse Carnot cycle, which is the ideal system, we're going to say, okay, what do real refrigeration units run off of? They run on, it's kind of like a reverse Rankine cycle, where we've kind of taken some of these ideal processes and made concessions to reality and said, okay, this is what we can actually do with real equipment and real components. It's not exactly a reverse Rankine cycle, because we end up using, instead of a turbine to do an expansion, we use an expansion valve. If any of you remember from looking at your refrigerator thing in intro lab, there's a compressor. We have a compressor. There's a evaporator, like a boiler. There's a condenser. And there's not a turbine, there's an expansion valve. And so we talk about in this video, how do we go through and look at refrigeration cycles? It actually, have any of you ever heard of, right, so most of us heat our houses, probably your dorm stuff, are heated with furnaces, where we take natural gas and we burn it. Sometimes we use space heaters where we take electricity and convert it with resistors directly into heat. Has anybody ever seen or heard of a heat pump for heating? You heard of a heat pump? No. So heat pumps are used sometimes in, most often they have been used historically in a little bit warmer climates where you don't need as much heating than here in Michigan. So they're not super popular here. Although newer models are becoming, are able to be used in Michigan, but it's basically a refrigeration cycle or an AC unit. That cold temperature is your house and the warm temperature is outside. In a heat pump, you do the exact same thing, but now this warm temperature is your house and the cold temperature is outside. So it's a way to flip an AC unit and turn it into a place where you're dumping heat into your house. And the reason that you would do that versus like a furnace or versus an electric heater, it doesn't take, you actually kind of get more bang for your buck. You're not creating heat. Like an electric heater, you're taking electricity and converting it to heat. In a refrigeration unit, you're not creating heat, you're moving it from one place to another. So you can actually move heat easier than you can create it. So you can find, like, essentially heat pumps, refrigeration cycles, they're not 100% efficient. They can be 200 or 300% efficient, or even more. So you get like a whole bunch of extra heat for the amount of work that you're putting in. So we'll go through and do some kind of some analysis of that in the videos and then also on the homework. But what we're going to spend the rest of today looking at is not either of those. We're going to, again, I said we're going to kind of start transitioning to a little bit more theory, but also hopefully stay connected to real tangible things. And we're going to do that by switching the types of systems that we're looking at. So far, we have looked exclusively at systems that are control volumes. What I mean by that, I'll just draw one, right? We have a system like this, right? We're getting work out. So this would be a turbine. And we're looking at a mass flow rate through that thing. And when we're, right, if we think about how we're doing the analysis, functionally, we're like taking a look at that specific region of space and saying what comes in and what is leaving, right? So in a system like this, work is generated or is extracted or supplied by an external device. Right, external device, a pump, a turbine, a compressor, one of these things that we've been looking at before. These are, as we've kind of seen, these are commonly used all over the place. In real systems, we have pumps and compressors and turbines. But it's helpful, especially if we want to understand a little bit more fundamentally what some of these different thermodynamic quantities, what they are, where they come from. It's useful to shift our perspective a little bit. And instead of looking at a specific region of space, we can follow a set amount of stuff. And we can watch what happens to this specific, amount of matter, this specific mass. So we do that using a control mass. By instead of viewing this region of space and things can come in and things can go out and different things happen like that. Now we're going to view a specific amount of stuff, and we're going to look at changes that happen to that quantity of stuff. So the big difference is I think it allows us to look a little bit more, to understand a little bit better what some of these quantities are. The big difference is that work becomes, right, so in a control volume, we had work was either happening because of like some moving mechanical part. It's kind of the same, but now it's not it's a moving system. Like the whole mass is either expanding or contracting. Right, so in a control mass, we're looking at a set volume of stuff. So if the pressure goes down, the whole thing goes up. So now volume can change. We're not looking at a set region, we're looking at a set quantity. So it can expand and contract, and that's where work is done. So work is done by the system right? And by system, I mean this control mass, this thing that we're looking at, by the system pushing against the surroundings. Okay, or we could flip that and say the surroundings can push against the system. So this is how we're going to define. Okay, how did we define positive and negative work before? Right, we defined it kind of by a steam engine. If we put heat in, that was positive heat. If we take heat out, that's negative heat. If we put work in, that was negative work. If we take work out, that's positive work. So if the system is pushing against the surroundings, this would be, that would be positive work. Or the surroundings pushing our system, that would be negative work. Okay, so we have kind of the same definition. It is the same definition, but it feels a little bit different. Where if we're pushing against the surroundings, that's positive, where that's getting work out. If we're pushing on the system, we're putting work into the system, that would be negative. Okay, so you may remember from quite some time ago when we first talked about reversible processes, I showed something like this, where, okay, so what was a reversible compression? It was a compression that happened as gradually as possible, right? Where our system is staying in equilibrium the entire time. We're compressing it, so we're adding, a single grain of sand on top of our piston, grain by grain by grain by grain, and slowly, slowly that's compressing our gas. This is a control mass problem. So we're looking specifically at the gas in that cylinder. Oh, didn't mean to do that. I think I must have pushed a button on my pen. All right. Are we back? We're not back yet. Whew. All right. So, so this is a control mass problem where we're looking at the specific the gas inside of the cylinder. That would be the region of space that we're interested in, and it can change volume as it's expanded or contracted. That's where either work is done on the system, as in this case, or the system, the gas, does work on the surroundings. You can see this is going to be a piston and cylinder. We're going to do a lot of piston and cylinder problems because it's an easy way to conceptualize what a control mass is. The control mass is the stuff inside the piston and cylinder. That's certainly not the only way the only way that control mass problems are relevant. They are relevant. We're going to use them to be able to look at something like an internal combustion engine. If we want to calculate the power from an internal combustion engine, we can use control masses to do that. And we certainly will, but they're useful kind of more broad than that. We'll use this as a useful way to picture it because it's, again, kind of easy to see what's the mass that we're looking at, what's the surroundings. So we'll use piston and cylinder problems quite a lot. Okay, so for this system, this type of a control mass, for work to be done, we'll put a star by this. for work to happen, either a positive or a negative work, anything non-zero, there must be a volume change. So this is one of the key insights from control masses. We have to have a change in the volume of the stuff for there to be any work at all. If there's no expansion, if there's no contraction, there is no work. If it's a constant volume process, work is zero. Right? You can't, there's no pushing. The surroundings are not pushing on the system is not pushing on the surroundings if the volume isn't changing, if there's not an expansion and contraction. Right? If we think about kind of a more basic definition of work, work is a force applied over a distance. So no volume change means there's no distance, right? If I push against this, but it doesn't move, I maybe pushed hard, but I didn't actually do any work. So the same thing here. There's no work if there's not a volume change. Just like in a control volume, we can have different ways that we go about it. I just showed you one where we did a reversible compression, or pretty close to reversible compression, where we added a grain of sand at a time. We could also do the, you probably don't remember this, but there was another example. Okay, what's an irreversible one where we throw a 100-kilogram barbell on it? And we don't do this one grain of sand at a time. We do it all of a sudden. That would be an irreversible process. Just like for a control volume thing, we could have a reversible turbine or an irreversible turbine. We can do the same thing with control mass problems. We can have a reversible or irreversible expansion or compression. For reversible work, we call this typically PV work. This is PV standing for pressure volume work. So for reversible PV work for a control mass, okay, so for a control volume, we said we could do delta S equals 0, and then we could do energy balances. That still works. We're still going to be able to do the same thing. The other way that we did it, right, we did this for liquids. We said we can just calculate the work directly from pressure and volume. And we got the integral of V delta P, VdP. So we got for incompressible liquid where V doesn't change, we had, let me just write this. So equals minus the integral of V dP. I'm going to put this in brackets so that this is just a note. This isn't a, it's going to look kind of like this, but not exactly. For a control mass, the reversible work, and well, I'm going to write it like this. I'm going to put little subscripts 1 and 2, 1 on the left side, 2 on the right side. I'll explain why I did that in a second. Is equal to minus the integral of PdV. I think I screwed up. It shouldn't be minus. It should be just the integral of PDV. So it looks almost the same, but the P and the V are switched. And that's with reason, but it's really easy to get those two mixed up. The reason that they're switched is we can get into it a little bit, but because it's, I guess we'll get into it later. Can I say that? And just trust me now that they're switched and they're supposed to be switched. It's because of enthalpy. Enthalpy screws everything up, right? Because it had this flow work, which was a pressure volume term in it. So that flow work term screws up other stuff. So this is a key equation for control mass problems. It's the work for an expansion or contraction. The W12 means the work along a specified path or a specific path from state 1 to state 2. So this is kind of like, okay, again, we're trying to connect this a little bit to the stuff that we've already done and you've all gotten really good at. When we wanted to look at the work of a turbine, we said we're coming in at state 1 and the turbine happens and then we leave the turbine at state 2. This is kind of the same thing, except they're going to be, it's not like a coming in, something happens and then we're leaving. It's going to be initially, we're here, something happens, and now we're here. So it's going to be, it's not like a space thing where we like have an inlet and an outlet. We're going to have an initial, things happen, and a final. So that's going to be the big difference for a control mass, again, because we're tracking the same bit of stuff throughout. So we're going to look at, okay, so where is that initially? Things are happening. What exactly happens? What is that process? And then where are we after that? Okay, we'll do one quick example. If we jump to this, and you'll see some examples similar to this in this week's homework. There will be a couple of them, and you'll see once you get the hang of them, they're really easy. Okay, so in this example, we have a piston and a cylinder. Like I said, we're going to deal with piston cylinder stuff quite a bit because it's relatively easy just conceptually. We have a piston and cylinder. It contains saturated liquid water at 100 Celsius. So it's 100% liquid. And then we have to do work to partially vaporize the system to give a 65% quality mixture. And then we're told something about how does that happen. It is a constant pressure, quasi-equilibrium, or reversible process. So those two words here at the end, quasi-equilibrium. Quasi-equilibrium means that this is one of these really slow, gradual type processes where everything is, all the forces in the system are balanced. It's just like another code word for equilibrium, or a code word for reversible. So when you see quasi-equilibrium, right, this just means reversible. Okay, so let's draw out the process as to what's happening here. Okay, so in our example, we had a an initial state, which I'll call state 1. We have, this is my piston cylinder. So there's my cylinder and a piston. And this was filled with entirely liquid water, right? We had initially, it tells us that our temperature is 100 Celsius and that it's saturated. So X1, it's a saturated liquid. It's 100% liquid. It's right at the boiling point. So X1 is 0. And we're told that we go along, what kind of process is it? It was a quasi-equilibrium or a reversible process, also a constant pressure process. So again, if we go back, we have a constant pressure, P1 equals P2, and this is reversible. And we're going from that initial state to our final state or our second state. We've gone through an expansion. So there's our piston and cylinder. Caution, things are not drawn to scale. But at least, I think some of these sketches at least give us an idea of what's happening. And our final state, and I'm forgetting from our picture here, our final state was, okay, it was constant pressure and 65% quality. So we're told, okay, so this is our final state 2. We're told that X2 equals 0.65. So if we think about what that means 65% by mass is vapor. That means we've gone from this to, right now we have liquid and vapor. Again, not drawn to scale. If I were to draw this to scale, the liquid would be a tiny little puddle and the vapor would be huge. But at least gives kind of a ballpark idea of what's happening. Okay, so if we look at trying to solve this problem and trying to figure out how much work did we get out of the system, this is an expansion problem. So our system, the liquid, is expanding and pushing against the surroundings. So that's a system where we're getting work out. That's going to be a positive work system. And if we look at trying to calculate that, we're going to use W12 equals the integral from state 1 to state 2 of P d specific volume. And I apologize, that's kind of getting kind of low on the board there. Okay. All right, so we have to figure out, like we've done in control volume problems, we can use some of the things that we know about the state. We can look up, specific volume and entropy and enthalpy and internal energy. We can look up whatever we need to. And same thing at state 2, we could look up things that we need. So we know if we wanted to look up, we could look up that the pressure here at state 1 is 101.3 kPa. We could also look up the specific volume. Specific volume is 0.001044 meters cubed per kilogram. So we know two things, we can look up the rest. If we know those two things, we do know from our process that P1 equals P2. So we can say that we know that P2 equals 101.3 kPa. And we could look up our specific volume. Now, in this case, we would have to use right, V2 equals Bf plus X2 VFG because we have equality. So we'd have to go through and do that calculation. If we did that, we would find that the specific volume is 1.088 meters cubed per kilogram. And now you can definitely see my poor drawing skills because I drew it like expanding maybe a factor of 2, when in reality we expanded a factor of 1,000. Right, vapors takes up a lot more space than liquids, especially at low pressure. So in reality, we expanded a factor of 1,000. I drew it about a factor of 2 because caution, things are not to scale. Okay. If we want to do this though, and we're almost done here because these problems are quite simple, we can use this for, again, this is for reversible, for a reversible process. This happens to be a reversible process, so that means we can use it. The handy thing is that our pressure happens to be constant. So this equals P times the integral from 1 to 2 of dV, because P is constant here. So because of the specific way that we're doing this, this is a constant pressure system, so we can take pressure out of the integral. And right, we can solve this integral. This is equal to P delta specific volume. And we can go down and solve this, that the work from state 1 to state 2 equals pressure, delta specific volume, which is pressure. Instead of out minus in, it's final minus initial. V2 minus V1. And we can plug numbers into that. That's 101.3 kPa times 1.088 minus 0.001. And that has units of, sorry, I'm running out of space. This over a little bit. That is units of meters cubed per kilogram. So now the only thing that we need to do is plug in those numbers and do some basic unit conversions. These units here are kilopascal is a kilojoule per meter cubed. So you can see functionally the meters cubed that would cancel with that meters cubed. So we would get that the work from 1 to 2 is about 110 kilojoules per kilogram. And if we knew how much mass we had, if we had, say, a kilogram, we could know exactly how much work it took, how many kilojoules. So we're going to stop there for today. There are right, this equation, this guy here, that equation works regardless of the path, so long as that path is reversible. We'll talk later about what do we do if the path is not reversible. But we can go constant pressure. We could do a constant, kind of a varying pressure if pressure is changing. How does that work? We'll go through a couple different examples of different paths that you can take. These are going to be the last 3 problems in this week's homework assignment. I just want to make a special note. They're like this. It takes more time to draw out the problem than it does to actually plug in the numbers. So they won't take you that long. They're just like simple one-step things. Make sure you come to class next week with those finished, because we're going to take those and then extend on them and say, how do we take some of this stuff from work and then use it to do energy balances and figure out some other things about some of these systems. So take those, the last 3 problems, like normal, the assignment's not due till next week at 9. But those last 3 problems, they should be really quick. Make sure you get those done for class time next week. With that, it's 9:51, so I'll stop talking. I'll hang around if there are any specific questions. Otherwise, we'll see everybody next week.